Rajkalkar, and I am very much excited to share my internship experience in embedded systems. And over the past months, I worked extensively on microcontroller programming, real-time interfacing, and embedded application. So this presentation will cover everything I learned, including the theoretical concept and the project which I have done, and include the key technologies which I have explored. Thank you, Emertxe, for giving me chance in internship. It is very helpful for my ENTC branch. So, what are embedded systems? Embedded systems is dedicated computing systems designed to perform specific tasks as part of a longer system. Characteristics of embedded systems are known for low power consumption, real-time operation, high reliability, task-specific functionality. And the applications are they are widely used in automotive systems, medical equipment, consumer electronics, and industrial automation. And the components of embedded systems is a microcontroller and microprocessor. They are act as a main processing unit in embedded systems. Memory used to store program instructions and data. Input and output devices include sensors, switches, displays, and actuators for interaction with environment. Power supply and clock circuits ensure proper operation by providing stable power and timing synchronization. Communication interface protocols such as SPI, I2C, and UART are used for data communication. What is microcontroller? The microcontroller is a small integrated circuit designed to perform or control a specific task or operation. It consists of a CPU, memory, input-output ports, timers, and communication interfaces on a single chip. Popular microcontrollers. Common examples including PIC, AVR, ARM, Cortex-based controller, and ESP32. Microcontroller architectures. Von Neumann architecture and Harvard architecture. One human architecture uses a single memory to store both program instruction and data. Instructions are executed sequentially and simple design but slower due to the memory bottleneck. Hardware architecture use separate memory units for program instruction and data, allows parallel instruction execution, and provide higher performance and widely used in embedded systems. MPLAB ID and development environment. It is a software MPLAB ID means integrated development environments used for designing and programming PIC controllers. X8 compiler is a C language compiler usually specifically designed for 8-bit PIC controllers. PixSim Lab Simulator. It is a simulation tool used to test and verify PIC controller projects before implementing them on actual hardware. PIC 16F877A microcontroller overview. Its architecture based on 8-bit RISC architecture for efficient instruction execution. Features are include strategic unit output pins, multiple timers, and inbuilt ADC and communication interface such as SPI, I2C, and UART. Application commonly used in motor control systems, industrial automation, and sensor interfacing application. Peripherals used in the project. Switches and keypads used for user input and control operation. CCL display is used to display messages, status, and timing information. Timers and buzzers. Timers are used for time-based operation, and the buzzer provides audio alerts. Ports and pin input-output configuration. GPIO means general purpose input-output ports used for interfacing input and output devices. Pin mapping for PIC16F877A. It's an assignment controller pins to specific functions and peripherals. Data and input-output configuration. It's settings the pins to operate as digital and analog inputs and outputs. Tactile switches in embedded system. It is defined as the tactile switches are mechanical input devices that give a noticeable tactile feedback when pressed. It has working principles. When the switches is pressed, it completes the electrical circuit and generates the input signal for the system. Application only used in control panels, remote controllers, keypads, and industrial automation systems. Interfacing with PIC16 F877. The tactile switch is connected to GPIO pins configured as digital inputs to detect user key presses. Interrupts in embedded system. The definition of interrupts enable a microcontroller to respond instantly to internal and external events. There are types of interrupts, external and internal interrupts. External interrupt means generated by external events such as button presses or sensor signals. And the internal interrupts are generated by internal modules like timer, ADC, convergence, and communication peripherals. ISR, like interrupt service routine, a special function that is executed automatically when an interrupt occurs. It has application also, widely used in real-time systems such as motor control, sensor monitoring, and automation systems. And next is timer in embedded systems. Timers are used to create time-based delays and trigger events. Types of timers: timer mode, counter mode. There are two modes. Timer mode counts internal clock pulses to generate accurate delays. Counter mode counts external events such as pulses from sensors. Interfacing with PIC16 F877A in timers. So timer 0, timer 1, timer 2 are used for various timing applications. Applications are the timer are commonly used in motor speed control, periodic data logging, and signal generation. Interrupts in sorry Prescaler and postscaler timers. Prescaler divides the input clock signal for it is applied to the timer. Postscaler divides the timer overflow output before and interrupt its generator. Significance is the prescaler and postscaler helps obtain accurate timing intervals without the need for high frequency clock sources. And the example of implementation, different delay periods can be achieved by configuring prescaler values in timer 0. LCD interfacing in embedded systems. An LCD is used to provide visual output in embedded systems. Like common LCDs are 16s to 2 character LCDs and 128 into 64 graphical LCDs. Interfacing with 16 F877A. Data and commands are transmitted using either 4-bit or 8-bit interface modes. There are applications. LCDs are widely used in embedded graphical user interfaces, industrial displays, panels, and monitoring systems. Key learning. Embedded system programming skills. Gain experience in writing efficient and optimized firmware for microcontrollers. Hardware interface knowledge. Learn to interface with keypads, timers, PCBs, and actuators. Debugging and troubleshooting. Develop the ability to detect and resolve hardware and software related issues. Real world application development. Hands on the experience by implementing practical project used to use the PIC method 77 microcontroller. I2C communication and embedded systems. I2C means an inter-integrated circuit is a serial communication protocol that uses two wires for data transfer. It uses SDA and ACL to enable synchronized communication between devices, and each device connected to the I2C bus is identified by a unique address. I2C is commonly used in EEPROMs, temperature sensors, and real-time clocks. Watchdog timer in embedded system. Watchdog timer is a safety timer that automatically resets the system if the program stops responding or crashes. The importance is helps prevent system failures and improves overall system reliability. And the application is widely used in industrial automation, medical equipment, and other safety critical systems. And now we are talking about our project in embedded system, that is a micro one. The project name Embedded control-based micro aim is to design and develop a micro control system using a microcontroller. The microcontroller name is PIC16F877A, and we use hardware components that is keypad, LCD screen, buzzers, relay module, heating unit, cooling fan, timer circuit. Micro project has working principles that is user input. User set the cooking time and power level using a matrix keypad. Control process. The microcontroller controls the timer, relay operation, and heating elements based on the selecting setting. And the display is 16:2 LCD display. Safety mechanism is a buzzer provides an alert in case of overheating or abnormal condition, and also use a cooling fan when we need it. Future scope and enhancement. IoT connectivity allows remote monitoring and control through the mobile application. Touchscreen interface. Replacement of physical keypad with an interactive graphical display. Intelligent cooking features. AI-based algorithm for automatic adjustment of cooking timer and temperature. And power efficiency is advanced.
So let's begin the demo. So before you see the project demonstration, let me open MP-Lab. So I wrote the code for the macro one using multiple source files. So this project consists of so many files. So before you see all the files, let me give a brief introduction of the files which I have used. One is main.c and main.h, where our source file are the header, so which handles system initialization and peripheral setup, and the main control loop, and the micro 1 c micro 1 dot, which manages the core functionality of the microwave, including the mode selection and process execution, and CC dot and CLC dot, which controls the LCD display, handling message and status updates. And we have the ISR dot, which is implement interrupt services routine for safety mechanism and real-time operations. And I have matrix keypad dot c matrix keypad, so which processes user input from the keypad, allowing selection of cooking modes and the time adjustment. And we have the timer dot h, which manages the counter timer, ensuring accurate cooking duration. So now I will walk through the key section of the code. So in main dot, the microcontroller is initialized and the peripherals such as the LCD keypad and the timer are configured. The main control loop continuously monitor user input and system status. And in the micro and dog, the different cooking modes like microgrill and connection are handled based on user selection. The appropriate function are called the adjust cooking, power set timers, and activate heating elements in the CLC doc file. Ensure that relevant messages such as like powering on microwave one mode selection and countdown timer are displayed correctly on the LCD. ENP handling in ISR dock ensures safety by stopping the macro if the door is open. So the timer function in timers do ensures precise countdown operation. So now I will compile the code to ensure there are no errors. Once compiled successfully, X file will be uploaded to the P16F87A microcontroller. After uploading, the system is now ready for demonstration. Right. So once we are writing with the code, we can go to the projects. Right click on the to the microphone, select the clean and build. Then the output will be appearing like clean successful. If there are no errors, then we will getting a warning, but we can neglect those because at the end, if you are getting build successful, if it is build fail, then those warnings error you need to clear, you need to rectify. But now project is built it successfully. So once we compile successfully, the X file will uploaded to the microcontroller. It's P16F8 7A microcontroller. Now, before I uploaded my macro over project code, let me first introduce to PiximLab, the simulator which I am using in my project. Now, why use a simulator actually? So, when developing embedded systems, testings directly on hardware can be difficult, and even there is always risk on damaging components, right? And even debugging can be time consuming. So that's where PiximLab comes in. So it is an open source simulation platform that allows us to test, debug, and refine microcontroller based projects without needing any physical hardware. So, what is the Pixim Lab? So, Pixim Lab is a microcontroller simulation environment that emulate different microcontrollers like the P16 F8 7A and the P18 F452, which are commonly used in embedded systems. So, with this, we can test our embedded C code before flashing into the real microcontroller, and even we can simulate peripherals like LCDs, keypads, buzzers, and relay, and we can debug errors safely without damaging real components. And even we can quickly modify and test code without rewiring circuit, and we can also analyze circuit behavior and verify logic be before deployment. So, using PiximLab, I can show you how the micro oven works step by step, just like a real hardware prototype, but without needing a physical setup. So now let's make a closer look at the simulator and find its different part. First, if you see the top left, that is green screen area, which is called LCD display, liquid crystal display. So here this is a 16 cross 4 character LCD based on the HD44780 driver. So it is used to display system messages, and next bottom left number pad 1 to hashtag. So those are called matrix keypad. This is 4 into 4 matrix keypad acting as a user input interfaces. And next middle selection, you see small red headlights. So those area all LED indicators. So the LED represents the different status indicators. And the next top right near the fan, and heater labels, if you see, those are called cooling a fan and heaters. So the fan is simulated here to show how the macro cools down after operation, and the heater turns on during the cooking, and it is linked to the selected power level. And right side, two large white blocks relays. So these simulate the relay switches that turn on off the microwave heater and fan. So when I press start, the relay activates powering the heater. When I press stop, the relay cuts off the power supply, and the next near the fan and heater selection we have the buzzer. So this works as an alert system. It sounds when cooking starts or stops, when the cooking time finishes, when and occurs like. And the next bottom right we have black IC label peak 18 F452. So that is a microcontroller. So this is the brain of the entire system. So it runs the embedded C code that I have written in MPLAB. It is process input from the keypad updates and the LCD control relay, and the ensure safety mechanism works properly. And the next is, we have the bottom right blue button label reset. Yes, so if something goes wrong during simulation, I can press this button to reset the microcontroller and restart the program. That is reset button. And the next middle right we have IM35 sensor. So it is a temperature sensor. So this is also we have used. And We can also use in real world applications for automatic temperature based cooking, but here's the simulator just for a display. Now it's time for the demonstration. So let's begin. So first I load the X file into the simulator. To that I will click the file, then select load X here. I will choose the micron docs file, means the hex file, and click on open. Once the file is loaded successfully, the simulation will begin. Now let's observe the CCD character LCD. The display will show the messages powering on, micro on. So after a few moments, the screen will update the display. The four available modes, cooking modes, which are like micro mode, grill mode, convention mode, and start mode. So to select any of these modes, I will use the matrix keypad. So uh, any of these modes I will use matrix keypad. So let's say I want to enter micro mode, so I will press the corresponding key on the keypad, which is the case is 1. So once selected, the LCD will display with the default power level of 900 watts as programmed in the code. So next, it is asking for to set the time using the keypad. I will need to enter the time in minutes and seconds, right? So I want to enter the time limit of 10 seconds, 1 minute. So I need to press 1, then 0, then again 1, and here you see that star for clear, hashtag for enter, star for clear, in the sense if you press any other number, or unfortunately, like if you are wanted to enter 2 minutes, but you have entered 1 minute there. So to change that, we can have the option to clear it and again re-enter the time. So if you are confirmed and you are done with the re-entering the time, we need to press the hashtag. So after that I will start the micro system will activate and the fan will begin the operating while the countdown timer starts. And as you see there, so the LCD will continuously updating as you uh, see the timer there. They are so showing the remaining cooking time. Now we can demonstrate the pause and resume. As here you see 4, 5, 6 options like that: start or resume, pause or stop. So I will demonstrate the pause and resume functionality, how so pressing that pause will stop the countdown, and again you can press the resume button, which is restart. uh, so that is the demo. So let me press the button for so see the if restart the timer from where it was pushed, sorry, paused previously. So let the countdown complete between. If you wanted to stop micro manually, so we need to press the stop button, and there, so LCD will return directly to the main menu, allowing the user to select a new mode or set a new timer there. As you see here, now if we go for the grill mode, so we need to press the button 2. So same like that micro mode, inside need to set the timer. For example, I need to set the timer for just 10 seconds. So I need to enter 1 and then 0, then hashtag, and that is the enter. So again the system will activate. So that was the demonstration video I have done. Thank you, Emertxe.